All right. Hi, everyone. I wanted to make this small tutorial video on problem solving aspects of photoelectric effect. Now, as part of our previous lecture, हम लोगों ने we understood what photoelectric effect was. We understood it, qualitatively as well as from a mathematical perspective using this equation. Right. I reminded you that it's a one photon, one electron equation in the last class as well, and I'm reiterating that again over here. So in this, what we say or how we read this equation is that energy of photon that is striking a metal plate is being used in two parts. One is to eject the electron out of the metal atom. Right? We call that energy as work function and represent it using the symbol phi. Right? We call it as work function or threshold energy or binding energy or ionization energy or energy required to overcome the attraction between nucleus and electron. Like it can be spelled out in many ways. So one part goes in overcoming the attraction between electron and nucleus. Like one part of that energy of the photon is used in ejecting the electron, and then the remaining part of the energy of the photon is imparted to the ejected electron itself as its kinetic energy. Right. So यहाँ पर, as you remember, photon strikes on the metal surface and the electron is ejected. Now, as I said, in terms of problem solving, sometimes depending upon the data given in the question, you can have energy of photon, written as h nu or hc by lambda. And similarly, the work function can be written as h nu naught or hc by lambda naught. We did speak about what nu naught and what lambda naught mean. Like lambda naught was threshold wavelength above which photoelectric effect was not observed. Nu naught was threshold frequency below which photoelectric effect was not observed. And this corresponds to the frequency or wavelength of a radiation that would be striking the metal. Right? This work function, let me remind you, is an important property of the metal itself. Right? This is something which you can say it changes from metal to metal. For example, for a silver kind of a metal, it will be a different value. For gold, for copper, it will be a different value. And of course, you can write kinetic energy as half into mass of electron into the maximum speed of electron. Now, I told you the reason for why we use this word max over here, because in this equation, we are assuming that there is no other form of loss of energy, like all the energy that is coming from the photon is used in overcoming or coming out of the atom, and the remaining is imparted as kinetic energy. Now, just to take a quick tour of the problem solving method that was employed over here, you can try this question. I'm taking a pause. All right. Assuming you have taken an attempt, many of you would have been able to get the answer. So let's check out how we have to solve this question. Now, one of the key things that or learnings that comes from this question is the language, the ability of a student to comprehend the language of the question. Right? Sometimes you might get very explicit data, like everything spelled out, but sometimes it is written in a way that you will have to comprehend by yourselves. So in this question, minimum energy necessary to overcome the attractive force between electron and the surface of the silver metal is this much. So this is a fancy way of describing work function. Right? The work function was the energy that was required to eject the electron, and that is what this entire first line talks about. So here we get that work function is 7.52 into 10 raised to the power of minus 19 joules. Now, as a follow-on statement in the question, it is asking about the maximum kinetic energy of the electrons that are ejected, given that the radiation following, the radiation which is falling on the silver metal is of wavelength 360 angstrom. So we return back to our original equation of photoelectric effect. Right? We understand that phi is given to us, K max is being asked, and in terms of energy of photon, we are actually given the wavelength. Right? So we go ahead and use the formula of energy of photon as hc by lambda. Now, once we do that, it is really, really important for you to take care of the units. Like, please make sure that you are putting or substituting values in consistent units so that you will get a correct answer. So here, H and C are substituted in the SI units. wavelength, which was given in the units of angstrom, right? We are substituting it in the units of meters by doing the appropriate interconversion. And here, once we solve it, we get the answer to the kinetic energy of the electron, right, in the units of joules. Now, as you would have noticed, this is a cumbersome calculation, right? Every time when you have to solve photoelectric effect equation, like putting the value of H and C and then solving it is a bit time consuming. So here, notice karna, we have another unit which helps us to do calculations in a much more faster manner. And that unit is of electron volt. Now you remember in the last class towards the end, we did describe what electron volt was and how it was derived and defined. So assuming that you do remember the interconversion of electron volt into joules, 1 eV was equal to 1.6 into 10 raised to the power of minus 19 joules, right? You can simplify. This is what helps you to actually simplify a lot of your calculations. You can simplify the energy of photon, which we write it as hc by lambda, and then if we were to calculate, we substitute everything in SI units. You can just use this formula to write the energy of photon as 12400 upon wavelength in angstrom, and this will provide you the energy of photon in the units of eV. Now, how did I arrive at it? You yourself can try. Like, so you have this simple illustration in front of you, which can help you to understand how we arrived at this relationship. So let's say if I ask you to calculate the energy of a photon of wavelength 124 nanometers. So what you will do is you will have two options, either to use this formula hc by lambda or the EV calculation based formula. Both are going to work fine for you. Now, how we do it in the SI units is simple, straightforward. You substitute the SI value of H and C and put the wavelength also in the SI units of meter. You convert nanometer into meter. And then you solve for it and you'll get the answer in SI units, which is joules. Now, if you remember the interconversion of joules and EV, right? 1 EV was 1.6 into 10 raised to the power of minus 19 joules. So I can write 1 joule as EV upon 1.6 into 10 raised to the power of minus 19. Once I do that and simplify it, I get the answer as 10 EV. Now I can get the same answer by using this formula, like 12400 lambda in angstrom, right? Since the lambda was given in nanometer, so 124 nanometer will be 1240 angstrom. So I substitute over here and get the answer as energy of photon as 10 eV, right? So this is a technique which helps in solving the questions in a much faster manner. You will find that many questions in the booklet are going to be based on this, where doing calculations in EV will be much, much faster. To practice this, let me assign one more question towards using this electron volt unit and this formula of energy of photon. All right, so here's the question. Now, again, you can pause and try to solve it by yourselves. All right, assuming that you have now solved the question, let's look at the answer and use of this energy of photon formula in this question. So again, as I said, when we read the question, it is important for you to comprehend what is happening in the question and try to, articulate what is given and what is being asked. And in that process, if you are required to assume some variables, please go ahead and take them. Ho sakta hai those variables get cancelled out or those variables get solved for. So reading the language of the question, it says that when photons of wavelength 1240 angstrom, they strike a metal surface, the photoelectrons of maximum kinetic energy that are ejected have thrice as much kinetic energy as the fastest electrons ejected by a source of wavelength 2480 angstrom from the same metal surface. All right, so we try to now visualize what is given. Like, this is too much of English, so we try to break it up. So in the first scenario, what it is saying is that we have a certain metal on which we are striking 1240 angstrom radiation. And in the other scenario, we have the same metal, same work function, and we are striking 2480 angstrom 2480 angstrom radiation on it. Now, it says that in the first scenario, the kinetic energy of the ejected electrons is thrice as that of the kinetic energy of the electrons ejected in the second scenario. So let's say if I put the kinetic energy over here as K, this will be 3K. Now, we have in fact done, you can say 50% of the question. Remaining is now just forming equation. So you do remember what the energy of, what the equation of photoelectric effect was. And if you were to solve it in the unit of electron volts, then I would want to use the energy of photon as 12400 upon lambda in angstrom. And here phi will also be in EV and kinetic energy will also be in EV, right? Consistent EV units we are solving. So we substitute the values that are given over here and we form these two equations. Now, two equations, two linear equations and two variables. This is something which is pretty easy to solve. You can subtract or manipulate the equations or substitute and solve for phi and k. I'm not doing that right away. So I'm assuming that this much you know how to solve for. You get phi as 2.5 eV and kinetic energy as also 2.5 eV. So this was the part of the first question. What was the work function of the metal in EV? So we got the answer as phi is equal to 2.5 eV. Now, as part of the second question, you are being asked what is the threshold wavelength of the metal in angstrom. So you remember the relationship between phi and threshold wavelength? Correct. It was phi is equal to hc by lambda naught. Right. Now, if you would want to solve in SI units, then what you should do is convert phi into joules, right? 2.5 eV into joules, and then put H and C in SI units, and then get the value of lambda also in SI units. Or you could use the simplified version that we have. Instead of putting everything in SI units, you could write Hc by lambda naught as 12400 by lambda naught in angstrom, where phi will be then in EV. So you put the value of phi in EV and get the value of lambda in angstrom, which comes out to be 4960 angstrom. So I hope this quick tutorial helped you to grasp the concept of electron volt and how it helps in simplifying the questions of photoelectric effect. Now, as a follow-up to this, I would request you to solve certain questions from the booklet. The details of those questions, which questions to be worked on, I will share on the WhatsApp group for you to practice, and the same can be then discussed in the next class. All right. Thank you for your patience, guys. Take care.